Okay, so good morning, good afternoon to everyone who's dialed on to our generator monitoring webinar series today. One thing we just wanted to ask is, did you know the potential cost of having a turbine generator shut down due to a failure can be in the region of $300,000 per day? This figure can be much higher depending on the size of your generator. During this three-part webinar series, we'll delve into the key aspects of generator monitoring, highlighting the risks, the monitoring methods, and the data analysis. In this first of the series, we look at monitoring the effects of generator load cycling on stator winding conditions. In this session, you can expect to learn about the impact of renewable energy on baseload generators, generator winding failure mechanisms caused from load cycling, and online partial discharge monitoring for detecting load cycling defects. Now, I'd just like to pass you over to Nathan Jacob, who will run the presentation today.
Great, thank you, Seamus. Yeah, thank you for all those attending. So this presentation is an interesting topic. It's something that's come up more frequently that we've been attending some working group meetings, technical conferences. There's a general concern about generator stator windings and how their performance will be now that more renewables are coming onto the grid, and these traditionally base-loaded generators are going to have to augment their operating characteristics. So with that, we put together this presentation on monitoring the impacts from load cycling on generator stator winding condition. Okay. Just a little background. So myself, I'm a technical advisor at Camlin Energy. I was a test engineer with about 18 years of experience, and I was formerly at the Manitoba Hydro Test Laboratory here in Winnipeg, Canada. I am located in Winnipeg, Canada. I'm also an adjunct professor at the University of Manitoba. So my career, I've been fortunate to have a mixture of, technical focused work, both with like hands-on, but then also on the kind of deeper technical domain, understanding, failure modes and diagnostics to a deeper level, and the mix of academic and research with that as well. So very fortunate to have the kind of roles and experience I've had over the years. So as we get into it, some of this presentation will be focused around the North American US market. But of course, as we drive towards net zero globally, there's this sort of focus everywhere to ingest and optimize the utilization of renewable energy. And two key numbers that affect the US market that were published by the Energy Information Administration is that wind power is expected to grow by 11%, as we move in to 2025, from 2023 into 2025, and solar surprisingly up 75%. Now, what that looks like in the energy mix, so you can see, it's a very recent trend, but as we look at the generation capacity moving from 2018 into the present, very sharp rise in renewables, okay? And we can see in the graph here on the left that coal is falling, natural gas is kind of leveling off, but this rate of rise for renewables is quite dramatic. And that rise is being driven, largely based on increases on wind and solar. So as we consider the effect and the impact on traditional fossil fuel-based generation and even hydro generation, those are pretty static, okay? And it's really the onboarding of these new resources that's going to be kind of the dominant new factor in the operation of the grid, okay? Now, when we look at the actual utilization, so even though the capacity is increasing, we can see relatively tame numbers, through 2021 to 2023, where, although we look at wind and solar here indicated in green, it's only about 11 to 15%, 20%, going into 2025, that those are actually planned for utilization. So even though, and they'll represent a very large portion of the overall capacity, okay, so that's maximizing full wind generation, full solar. We know inherently that those resources are fluctuating in nature, okay? So what that means is that, that fluctuation has to be absorbed by the other conventional generation sources that are available, so both hydro and natural gas. Okay, so although we see the rapid rise in capacity, that doesn't reflect in actual generation in kilowatt hours that's distributed. Okay, so we kind of preempted that, but the operating changes, what that means for hydro and fossil fuel, obviously reduced utilization. That's an intended outcome. We want to reduce fossil fuel generation. Hydro, we want to optimize that as well, but those the wind and solar, when they're available, it's important that we maximize your utilization. Okay, we don't have the same capability at scale to store as we do with hydro. Okay, so given that, there's going to be operating changes imposed on hydro and fossil fuel-based generation, both in terms of the fluctuating supply, but also we need to support the grid with the conventional generation through supporting instabilities or potential instabilities. Okay, so both the fluctuating supply and the instability will need to be supported by load cycling of the conventional generation, but also running to provide grid support as, as support to the grid in case of system disturbances and that sort of phenomenon. So fluctuations in wind and solar, they'll require that fossil fuel generation goes into frequent operating transitions. So this is load cycling. So the force of going from high to low load in shorter periods of time. And the problem with that is that it leads to deterioration of these assets. The thermal stress that get imposed on the assets by forcing them from high to low temperatures and low to high temperatures again forces expansion and contraction to the actual physical components. Okay, and also the deterioration can be imposed just from mechanical fatigue. Okay, the fast changes in temperature, the expansion, contraction, but also the vibration that's ever present. These can lead to things such as deformations in the assets, as well as cracks to some components. And all of this can result in increased maintenance and reduced lifetime. So a generation that has been traditionally base loaded or at least predictably loaded, we can say even for hydro, even though they are normally cycled, between daytime loads and nighttime cooling of water for storage, they are also, as wind and solar become available throughout the day, will also be cycled more frequently. So this is going to be something that impacts both, hydro as well as fossil fuel-based natural gas generation. Now, when we consider the stresses, I know there's a lot of intuitions about what cycling can affect mechanical components. I think there's a greater inclination for understanding mechanical components. Cycling on and off is inherently stressful, but it's the stator winding is something that can be a little bit less intuitive and is something that is often overlooked. So we have here a figure from NERC showing failure rate data relating to the different components of a turbo generator. Okay, so you can see that overall the stator winding represents quite a large proportion of the overall failures. It's the second most frequent failing component next to rotating components. But like I said, the stator it includes the winding core and the clamping structure. So when we do consider the stator core and stator frame in with the winding as one entity, you can see actually that this exceeds the total failure rates for components, just the rotating components, and that would be the largest overall failure rate of any component associated with the turbo generator. So what are these effects? Okay, so when we consider mechanical fatigue, okay, mechanical fatigue, this includes all the components relating to the stator, the core, the frame, the clamping structure, and the laminations. And when we force a unit through frequent load cycling, for example, we can end up with situations where we have a loosening of the overall system because of fatigue and more consequential core vibrations. Fatigue on components, particularly like the clamping figures, can cause a lot of damage. You see here on the right panel two images. The upper image is one showing the effects of fretting. So here with movement of the core and vibration, that fretting is depositing um, rust and debris onto the winding end arm surfaces, which can compromise the insulation of the end arm regions. And even in a worse case yet, movement in the lower right picture, we can see the clamping finger actually missing. So just by vibration and embrittlement over time, the mechanical fatigue to those components, you can have breakages and losses of clamping fingers. And then this becomes a more serious risk. A clamping finger in the stator could cause a lot of damage if it catches between the rotor and the winding. And even just the abrasion, this movement causing abrasion to the winding surfaces can lead to shorter times to failure. Okay, and part of that is when you have this abrasion, this vibration on the winding surfaces, it can lead to removal of some of the semiconductive coating that's there to provide appropriate grounding of the stator slot, and that can lead to sparking discharge when you have that kind of abrasion. The load cycling also affects the internal insulation. So we just looked at external effects to the winding, but also internally there is an effect. This is something quite commonly understood. So there's actually a design type test for testing cycling effects on winding insulation. And it's something that's typically done as a test in laboratories to qualify a new winding design for a generator. These are described in IEEE 1310, for example. And the intention of the test, to simulate the load cycling, there's a test where you actually cycle high current through the windings. So if you see here on the right panel, here is a test setup at the Manitoba Hydro Lab in Winnipeg, Canada. And they cycle high current through the winding here. And that high current, what happens is the copper in the interior, it has a larger coefficient of expansion thermally than the surrounding insulation. So when that occurs, it can impose a stress at this junction to the bonding between the insulation material surrounding the copper and the copper itself. That expansion creates a shear stress. The expansion's in the kind of axial direction here. And then that shear stress can lead to voids when you end up with delamination at that junction between the copper and that site. Okay, so here's a sample photograph taken from a text, but you can see here, this is an image of thermal cycling effects where you have this separation that occurs between the insulation and the copper. And when that occurs, you end up with high electrical stresses at this region that leads to high partial discharge activities. And this can be one of the shorter times to failure within 4 to 10 years. Now, the effect of this axial stress and cycling discharge, thermal cycling effects can also cause a delamination between the slot interface for global VPI units. This is units where the insulation is actually impregnated into the core assembly with the windings installed. And it's important to have bonding between the slot section and the core. If that becomes delaminated, then you can have discharges at those sites as well. Okay. So load cycling is one component. The other to consider is the effect of operating as a grid support. Generators, if they are to support the ingestion of more wind and solar, we need spinning reserve as well as system support for the fluctuations. Okay, the fluctuation in supply requires that you have generations on the grid connected for voltage support as well as frequency regulation. And operating the generators in this way, it might not be intuitive, but operating something that is traditionally base loaded at a high loading level, if you're connected to the grid at low loading, sometimes this can have adverse effects, okay, for units that aren't normally operated in that way. Obviously, operation at low efficiency can impose more wear and tear. So the generators typically aren't as efficient at lower loading levels. Now, also there is a little bit of a coefficient of expansion of the overall winding within the slot. So at higher temperatures, things like vibration might be reduced. This is vibration of the windings in the slot sections. So if that vibration can be reduced at higher loading, when you back off and you're required to operate at low loading, there may be a slight contraction in the windings, and that may result in a looser winding. Okay, and loose winding is already a problem, like we discovered, like we discussed earlier in the talk, that vibration can lead to discharge at the sites within the slots of the winding. So also, for hydro operation, there's another factor to consider related to hydro. When you're operating at lower levels of loading, you may be forced to operate in a region where the generator operates a little bit more roughly. Okay, so and rough operation within the turbine rough zone can also lead to additional vibrations of the frame and core as well as the winding vibration. Okay, so all of these defects, the load cycling, the vibration effects from operating at lower loading levels, these can also affect partial discharges. And inherently, operating at low load, certain defects for partial discharges are also more active, particularly those that are related just to general aging of the winding and the aforementioned thermal cycling relating PD, which is related to the load cycling of the unit and the insulation system. So monitoring partial discharge, it is the best method we have for detecting stator winding defects. We see here in this figure from Seagray, the Seagray study committee SC11, looked at components that lead to failure within hydro generators, and insulation damage was the highest cause of failure. And if we look a little deeper, all of the normal defect modes that lead to failures of the generator windings, or the majority of them, can be detected by using partial discharge monitoring. Okay, so that kind of underscores the benefits of partial discharge monitoring in particular. And as we focus on PD relating to these specific defect modes, this is just going to reinforce why online partial discharge monitoring can be a very valuable tool in identifying defects which are associated with load cycling, running the units for grid support in this situation where we have to ingest more renewables. So the first one relating to loose bars and vibration here, this is, of course, just to re-summarize, this is related to thermal and mechanical fatigue. So fatigue of components like the wedging system or the bracing, this is attributed to the expansion and contraction of the winding with frequent cycling. And that can loosen these systems and lead to more vibration due to loose bars. Partial discharges relating to loose bars and vibration are generally well observed up at higher loads. So as there's greater magnetic forces imposed on the winding, if it's loose, we're more likely to see those effects in that operating region. And also abrasion relating to this vibration can lead to additional slot discharges that way. Now, for aging and thermal cycling stresses, we can detect these discharges being correlated to low temperatures. So the reason for that is at higher temperatures, sometimes there's expansion of the materials which may reduce the overall void size. And also at higher temperature, the partial discharge inception voltage is a little bit higher. Okay, so it's really operation down at lower temperatures that the partial discharges relating to aging or thermal cycling stresses would be more evident. If we operate at reduced load for grid support, therefore, if you have a generator that's not typically operated at low loading, this can be an accelerant for PD deterioration. Partial discharges, if they're persistent over time, will erode the electrical insulation. And then when you have some system disturbance, failure or fault at these defects become more likely. And aging and thermal cycling partial discharge also have their own distinct PD patterns. Okay, we'll talk about phase resolved PD patterns in a second. This can be an important tool for diagnosing specific failure modes and fault types. And The discharges associated with thermal cycling stress can also be similar to slot discharges like they were for loose bars and vibration if it is a global VPI insulated winding. So looking quickly here at slot discharges, we can see the effect of loose bars. And this is where thermal and mechanical stress on the winding have led to fatigue, which has introduced more vibration in the winding. And that fatigue could be associated with the wedging system, the bracing externally in the end arm regions, but also it could be due to just winding shrinkage. Okay. Partial discharge is correlated with high loading in loose bar situations. And this is intuitive because at the higher loading is where more magnetic forces will act on the winding, leading to more vibration. There's some thinking that when approximately 30% of the semicon is lost, that's where you run into a danger of failure being likely. And partial discharge characteristics for this tend to have larger partial discharge pulses on the positive polarity or the negative half cycle than they do of the negative polarity. And progression to failure can be quite quick in this case, roughly 2 years, okay? In terms of end winding vibration, we've already looked at some of these cases, but abrasion of the semicon regions can be quite a problem here. And failure can also be caused due to cracks in regions of the winding. We can see here a crack in the end cap, so some indications of movement of the winding at this location. And these can also be detected, the vibration and movement in the end winding regions can be detected with fiber optic vibration sensors. But this is similar to the previous defect of vibration in the slot. You can have short times to failure here as well. For the aging or thermal cycling type discharge, we want to detect these, by a distinctive pattern where they have, kind of symmetrical partial discharge patterns on each half cycle. The cause of this is when, just through normal thermal aging, it leads to debonding of the polymer, which causes voids distributed throughout the insulation system. And at low loading, if we're obligated to operate at low load for grid support, the discharge activity can be more repetitious in this situation, right? So the voids, they do result in higher partial discharge at reduced load. Now, conventionally, these would be quite long until failure, 25 to 30 years. But if a unit is already weak, if it's already well aged thermally and has voids in the winding, and we begin to operate these generators as grid support, then the progression of partial discharges may be accelerated by this kind of new operation with more thermal cycles and more operation at lower loading points, okay, for grid support. Now, the thermal cycling discharges, these can be detected by a distinctive pattern also. So higher partial discharge magnitudes associated with a positive half cycle. So with an online monitor, we would be looking for these types of patterns. And again, some of this is a little bit repeating what we've already discussed, but the starting and stopping operation leads to expansion contraction. And when we have delamination at sites close to the copper, these can be defects that lead to pretty short times to failure, between 4 to 10 years, okay? So with an online partial discharge monitoring system, it's not just, many would do standard conventional measurements where they do a spot measurement maybe at high loading. But as you've seen, some defects are more active at lower operating loads and temperatures. There is a dependence for the partial discharge activity based on the operating characteristics of the generator. Okay, so this has been identified in various industry standards and guides. The figure here from IEC 60034-27 actually prescribes measurement of partial discharges at various points within a procedure. So if you can, run the generator initially at low load and then increase the loading to a high loading point, you would repeat PD measurements there, and then again, once thermally stabilized, backing off on load, waiting for temperature to stabilize downward. So measurement of partial discharge at each of these operating points would help identify certain types of PD defects that could be associated or attributed to load cycling or operating to accommodate, renewables ingestion into the grid. So if this can be done passively, if you can have an online monitoring system that monitors each of the discharge activity at these operating points, we can then populate, a large number of discharge acquisitions at various points here on the operation. And each of these points of operation might reveal something informative about discharges in a specific region. Okay, so we can see here at lower load and lower temperature, the colored red data points indicate a higher discharge activity. So it's actually not in all instances up at the higher loading point, which is where generally I think many utilities perform their partial discharge measurements up at higher loading. But really, it's important to investigate the discharge activity and the intensity over a range of different operating characteristics. Relating specifically to monitoring for effects from load cycling, we can, focus specifically in the region here at lower loading and lower temperature. Okay, so at low temperatures, this is where we would most likely notice the effects from aging or thermal cycling defects. And if the defect is associated with loose winding and vibration, these would be observed up at the higher loading regions. So both of these are important to track and trend. And with modern online partial discharge monitoring, we can do this correlation. We can see where these defects are present. And then seeing where they are present, we can trend and we can make operating decisions that are appropriate for each generator at the time. If this is a bad generator for grid support because it has high PD due to aging and thermal cycling defects, then we may not run this generator for that purpose, and we may choose a sister unit for that application. So some key takeaways here. The accelerated integration of wind and solar is going to have operational impact for some of our conventional hydro and fossil fuel generators. Effects from load cycling and providing grid stabilization can have an effect. If we're making these operating changes, they can lead to more rapid deterioration for stator winding conditions particularly. And these degradation and these stresses are relating to the thermal stress, the expansion, contraction, the fatigue that leads to mechanically. And for mechanical fatigue, there's the thermal effects, but then there's also the vibration effect if a generator is obligated to run, particularly hydros, close to their rough operating zone. Online partial discharge monitoring for detecting stator winding defects, this will be the best tool. Okay, and if we can correlate partial discharge information with the operating conditions, this will be a very important tool for identifying what is the nature of the defects. And then that can inform maintenance. If it is a vibration problem, for example, this can tell us condition-based maintenance of maybe re-wedging or addressing some issues with lashing would be kind of the appropriate maintenance action to take. And online PD monitoring enables condition assessment, and by doing so, it improves overall reliability for the generator. And by providing early warning to these stator winding problems from load cycling, we're of course achieving that. Thank you. That's we can take some questions if there's time.
Hi, Nathan. Thank you for the presentation. It was very, very good. Thanks a lot. Yes, we have some questions in our chat. If you don't mind, I will go through. And I pick some of those, the ones I consider most interesting, and I put you in the order they came. So, first one. In the statistic that you presented for turbo generators, the failure in stator insulation is less than 50%. while for the hydro is more than 50%. Does it mean that PD techniques is more valuable for the hydro generators?
Uh, it's a good question. So if okay, so if partial discharge techniques are more appropriate for hydro than turbo are more valuable. So I guess one distinction is for hydro units are frequently cycled. Okay, so a lot of the developments for the testing and online partial discharge monitoring, many of those diagnostics were applied for hydros uh, first historically. There was an emphasis on hydro monitoring because there is more frequent cycling. Um, but to answer the question, if the failure rate is more skewed towards hydro failing in that way than it would be for turbos, it's difficult for me to say. The data is they're quite different mechanically, so to kind of evaluate that, um, the mechanical reliability and those components also factors in comparing apples to apples. Uh, I do think that certainly if more large turbo generators will be cycled, there will be increased stress, especially because the bars tend to be much longer. So the axial stress due to the expansion of the copper, there'll be more expansion of the copper overall. So hydros which are required to pool and cycle in this way day to day, um, I think some of that elevated concern and attention that's paid to partial discharges on those types of assets may be elevated here for turbo generators as well.
Okay, thank you. Next one. This is a customer or one of our followers who's using offline periodical test, and is saying that he performs offline measurement at PD measurement at each machine major outages. Does it mean he cannot see all the defect based on what you explained about performing the measurements at various condition of the generator? So,
Yeah, I mean, I believe so. I believe that just because of the way that customers approach the periodic test, many times the decision is to perform that test at a high loading point. And I think that some of the defects that may be related to operation at lower loading points, like thermal cycling related discharge, those would not be as well observed by that approach. So I I think that while it's possible to do the periodic test at the different operating points, it's not something that is practical, and that having an online sensor that can do the correlation and provide that information automatically would be a much bigger benefit.
very well. One last question. It's not the only one, but there are others, but we don't have much time. So, this is someone who has some experience with partial discharges, and is saying, how can we set up reliable alarms um, changing if PD are changing with operating conditions? How can we avoid false alarms? It's quite a
Yes.
specific,
Yeah, so,
technology.
so that's a very good question. That's something we've considered in our technology. So if you can have alarms that are configurable for different thresholds with different operating characteristics, this would allow you to have this kind of flexibility. So for example, if you configure alarms which are temperature dependent, this would allow you to have sensitivity to defects that are, more prevalent at low temperatures. And similarly, you can separately have another alarm configured for higher temperatures. So if you have, for example, high void discharge when the unit comes online, that threshold could be set a little bit higher, And then once you reach a thermal stability at higher temperatures, you could have a separate alarm with more sensitivity up at that higher temperature operating point.
Very well, thank you. Now I think Seamus, you want to tell something about the next session?
Hi everyone, Nathan, thank you again for the presentation today. Thanks to everyone who's dialed on today. Just a quick reminder that part 2 of our generator monitoring webinar will be held this Thursday, where we'll be looking at interpreting data from generator online partial discharge monitoring. To anyone who unfortunately we didn't get around to answering your questions today, we will reply to you all individually. Don't hesitate to reach out to any of us with any questions or any feedback. You can find my email contacts in the chat section, so please send any questions or any feedback you may have to myself. Thank you once again for your participation. We hope to see you again on Thursday. Thank you.